Good afternoon, London, I would say. How's everybody doing? Come on, it's been a long day. I know you want to go home. I had to go to parties, right? Come on. But before you're doing that, shall we make our session optimizing metrics collection and serving when autoscaling large language model workloads as a warm-up of your fun time? My name is Vincent Hou. It's my honor to team up with
Hey, my
Jiří
name is
today.
Jiří.
I'm a senior software engineer working with Bloomberg. My team is specialized in building and maintaining AI inference platform. I've been the lead of Knative operation workgroup for 6 years. I've been evangelizing open technology and contributing to open source projects during the past 10 years, maybe more, like OpenStack, OpenWhisk, Knative, Kserve. But don't worry, we'll focus on the 3 dots today. Jiří?
Yeah, so my name is Jirka. I work on a cool company called Kedify, where we try to do production-grade Keda. And I'm also a contributor to the project called KAGB. I like open source 3D printing. And you will see me in the second half of the session. So see you.
Okay. Thank you, Jiří. This is our agenda for today. We'll start with how, in general, autoscaling works, horizontal autoscaling works in Kubernetes, and talk about the challenges with large language model workloads, and the existing autoscaling solution in the market, and how we optimize the metrics collection and serving with our solutions. In the end, we'll run a demo. Previous episodes in KubeCon, tell me why and tell me why. I'm sorry, I cannot sing here today. You still carry many questions about how we can scale large language model workloads and what kind of metrics we can leverage. Have fun time on that stage. And thanks to these awesome folks I met in Salt Lake City, Ashok from Google, Lumila from Microsoft, and David from Red Hat. After attending their sessions, my confusion was resolved a lot. I put the links over here to their talks. You can refer to later. OK, for our session, as it's in London, shall we do something special for London, huh? To be or not to be, I am gonna do it. Act 1. Autoscaling is heavy and light, bright and dark, hot and cold, sick and healthy, asleep and awake. It's everything except what it is. Oh, it is so complicated. In cloud computing, autoscaling is a method to dynamically adjust the resource based on the load automatically. In Kube, it means a feature that allows the cluster to increase or decrease the number of pods or adjust the pod resource in response to demand. We have HPA for horizontal scaler and VPA as a vertical scaler. But we'll focus on the horizontal autoscaling in Kube today. Why do we need autoscaling? Because we would like to efficiently leverage, use our resources without influencing the service uptime performance. Neither of them is good, over or under provisioning. This diagram will show in general how autoscaling works in Kubernetes. What we can scale based on is something we can call metrics. Metrics have a broad range. They can be the basic resource like CPU and memory. They can be the custom metrics exposed by our workload. And they can be metrics that possibly come from outside the workload. OK. Metrics that need to be collected and saved somewhere. Well, we call it metric registry. After that, we need to make sure the metric can be consumed by the HPA. Otherwise, it has no meaning. And that is what the metric server is doing right over here. On one end, it can discover and aggregate those metrics from registry. On the other end, and make sure that the HPA can read the metric from it. So once the metric reaches the HPA, you run some calculation, maybe easy, maybe complex, and compare with the target value and make scaling decisions. That's generally how autoscaling works with Kube. Act 2. By my head, here come the challenges. By my heel, we care not. Sorry, wrong line. By my heel, we care a lot. Not. In Kubernetes environment, actually, especially in my company, Bloomberg, we build on-premises AI inference platform empowered by Kserve. Kserve makes the model highly scalable as a service, as it is a standard cloud-agnostic model inference platform to serve both predictive and generative model on Kube. Now it's an independent project, but it's on the Apache license, and it's on the way to become a CNCF project. Well, my mission was to build the auto-scaling solution for large language model workloads with Kserve. However, the large language model workload has brought us a paradigm shift in terms of what? OK, compute resource. We used to use CPU, now we use GPUs. And at the same time, the metrics also become different. Something that worked before but doesn't work right now. For example, default you could use like CPU or memory to scale something, but they do not reflect the usage of GPU. And later, we got another metrics like the number of requests per second. But this also doesn't reflect the GPU usage, latency, or throughput either. And speaking of some criteria that we can auto-scale the large language model workloads, we can think of either latency or the throughput. But in general, the problem is that none of the existing workloads auto-scaling metrics can fit our needs. So I say, projecting back to this diagram of how autoscaling works in Kubernetes, we got like I would say five group of questions we need to address. So one, we need to figure out where to read the metrics and what kind of metrics we can leverage to scale our workload. And second, we have no idea where to save them. And that's probably what the metric registry is. Three, we need to find out what can be used as metric server to discover these metrics and serve them to HPA. And four, large language model usually can be very large. Yeah, that's what they call large. It could be over 100 gigabytes or something. So how can we make it load and scale fast after the metrics value has been changed? Well, can we even configure how fast we scale our workloads? And five, is there a solution that is flexible and more portable to all kinds of platforms? All right, Act 3, and trust me, love, in my eyes, so do you. Dry sorrow drinks our blood. Oh, doesn't sound quite well, man, huh? Well, speaking of the existing ways of doing auto-scaling, well, let's start from the easiest one. No, that's it. We try to leverage the metric server. The benefit is that it's an integral, that's a Kubernetes native component that can scale very fast by leveraging small amounts of resources. It can read the metrics from the kubelet and export to the HPA directly. But the limitation is that only CPU and memory are supported. Second, this is a good thing. This is a good project. As one of the dependencies for Kserve, Knative serving implements its own Knative pod autoscaler to directly control the number of pods. It can scale based on the number of requests per second, and this metric can be collected by either queue proxy, sidecar, or the activator components. The number of the requests can change very fast. Well, it can be reflected in the KPI very fast as well, because no matrix pooling is involved. You always push. Once there is a change, KPI got to change immediately. And it can scale down to 0 as well, scale workload down to 0. Well, but the following drawbacks just make it impossible for us to use it. One, RPS, requests per second, does not work for large language model. Second, the complex algorithm or calculation has to be maintained in the source code. Third, to extend this model, this architecture with more metrics, we have to write our new plugins. Four, the RPS metric is associated with Knative only and cannot be ported to other platforms unless you use it. Third one, this is going to be more interesting. Recently, the virtual large language model community has announced the AI Bricks as the cloud-native solution optimized for deploying, managing, and scaling large language model inference. It supports both matrix-based autoscaling and optimizer-based autoscaling. It implements autoscaling in a similar way to Knative serving. And all the large language model metrics can be blended into this APA to control the number of paths. Well, these are all good, very good. But the limitation is that Kserve is the backbone of our inference platform. We cannot leverage this solution that's unable to integrate our platform. Walking through those challenges one more time. So, what's the source of the metrics and what kind of criteria to auto-scale a large language model workload? Well, we have the answer. The source could be the workload itself, as long as my workload has exposed the metrics as a path/metrics. Kind of permission standard, no worry about that. And we can scale, either think of is more latency sensitive or throughput. Yeah, those kind of two standards. So second question. How can we scale it fast or in a configurable way? Well, we can try to leverage the lightweight components, as many as possible, using a pushing mode, not the push mode, not the pulling, the push mode, not the pulling mode, as much as possible, I think. And most importantly, we can make it scale fast because there is a very nice feature called model cache, which is implemented in Kserve. But the answer to the rest of the question still remains unknown. What can we use for the metrics registry or server? How can we make it flexible or extensible? Once there are any kind of changes, we don't know so far. The thing is that we do not try to invent the wheel. We try to stand on the giant's shoulders. So who are the giants? And can we find them? When can we find them? So Act 4, as if it be now, it's not to come. If it be not to come, it will be now. Wow, good news. Optimization of metric collection and serving. We'll show you how. Jerry, stage is yours.
Thank you, Vincent. I don't have any Shakespeare lines for you, but thanks for the great intro. And state of the art, yeah.
I don't know.
So one of the giants, to continue with the analogy, is OpenTelemetry. Are you guys familiar with OpenTelemetry? Yeah, there are a lot of booths out there having the logo on them. So it's like standardization effort, umbrella / sets of standards for traces, metrics, and logs, right? And they've got some handy utility called OTel collector, which we'll be using a lot. So another one is a KEDA. I've got conflict interest because I work on it, but it's great, right? It's built around scale object, which is a custom CR that points to a deployment or any scalable resource. And the main benefit compared to pure HPA is that it can scale things to 0, but also it has multiple different ways to plug metrics in. So it doesn't have to scale only based on CPU or memory, but basically based on anything. And the third part we'll be using is my own contribution. It's Hotel add-on for KEDA. And this thing actually bridges the gap between the OpenTelemetry world, when you have these hotel collectors that forms kind of pipelines. We have some receivers, processors, and exporters. And this guy can listen to those and other exporters. So it contains OTLP receiver in their terminology. So it's kind of a sync of those metrics. But at the same time, can talk to KEDA and can scale and can advise KEDA the scaling decisions. It also contains short-term memory storage for a couple of data points. So it's like really small Prometheus, really lightweight Prometheus crafted just for scaling. Because that's KEDA also can incorporate Prometheus metrics. But the issue with this setup is that Prometheus gets overwhelmed. And imagine a scenario where you have a Grafana setup and also like alert manager. And if you use Prometheus with this scenario, also for scaling, it's overwhelmed. So there's the reasoning behind it. Our setup looks like this. Oh, this is like one of the possible setups. When we have one OpenTelemetry collector scraping the replica pods with models, this is the bottom left segment. And this sends the metrics to Hotel add-on, from which KEDA takes them and scales the number of replicas of the model. Another possible setup is this one. When we plug a hotel collector to each pod using a sidecar model. And this setup is a little bit better because it can react more quickly, and we can leverage the OpenTelemetry operator to help with the setup. So without further ado, let's check the demo. So is it visible? Yeah, cool. It starts well. I don't have network. Oops. Nice. So let me check the Wi-Fi. Live on stage. I will create a setup. I will create a hotspot. Yeah. I will use my own Wi-Fi. Hopefully it's gonna work. Oops.
Oh, we do that live demo, right?
Yeah, it's live demo. It's a live cluster running in GCP. Yeah, it works. First problem solved. So we have a Open Web UI pod, which is a Web UI to LLMs, and Llama version 3 deployed in our cluster in GCP. Just to convince you, we have a ingress resource called LLM web kremser.dev, and I'm using the same URL in here, so I can talk with the model. Hey, I am on KubeCon and Wi-Fi is not great. And it responds with something. But I can use also curl API to talk with the model the same way. So this is basically the OpenAI HTTP protocol. There is stream equals true or false. If it's true, the model will start sending the tokens in a stream fashion. So it responds more quickly. So if I do it, it's doing the same thing as we see before, but in a command line, right? This max token actually denotes like how long the response should be, and this is actually the thing that makes the request different, because one client can ask like short answer, the other one can ask for multiple pages of responses. If I set the stream to false, it works the same way, but it waits a little bit longer, but then returns everything at once, right? We'll be using this curl or this HTTP API to create some pressure to our model to be able to scale it. Like, what's the criteria? Why, or not why, but what's the scaling decision we will be using? We will be using internal metrics from the model itself. We are using VLLM runtime, and they exposes some GPU stats around the system. So we'll use KV cache in particular, and in the next part of the demo, we'll use also the waiting queue for the request. So let me first port forward the request from the model. This will share the metric endpoints from one of the replica pods. If I'm basically curling the metrics, because now it's localhost, right? And grabbing 2 of them, which we will be using. It's 0. Let me split the screen. And I can also describe the scaled object. So scaled object, remember, is just the thing from Keda that has a target deployment that it's scaling. So describe so model. It has something called where is it? Scale target ref. The reference is the deployment. In our case, this is the model. And this part is actually PromQL-like syntax. It's not full-blown PromQL. And it is sent through our Autel add-on, where it's evaluated and the correct metric is returned, correct metric value is returned. We don't support full Prometheus syntax because it's crazy, right? And there are ways to overcome this issue. We are using processors in Autel world. For instance, Keda wasn't able to work with float values. So what we did here is we scaled the value by multiplying by 100, and it worked. And this multiplication is done in the Autel collector itself. I can also show you the OpenTelemetry CR, which is responsible for OpenTelemetry operator injecting the sidecars to our models. Oops. And this guy contains the configuration for those small sidecars Autel collectors. So, for instance, this is the target address where we send the metrics. This is the Autel add-on. This is the filtering part. So we are interested only in those 3 metrics. And this is the part where we manipulate the metric a bit to multiply it by 100. In the next release of Keda, it will be fixed, and it will also support float values. Right, so now let me do some load on the server. I will be using hey command, which is basically creating 300 threads, and we'll be doing post request the same request as we saw before. This is the biggest difference. It has 4K tokens, so it's much more pressure. There will be much more pressure on the GPU. So if I do that, we should start seeing the metrics coming up. The top line is the number of requests being queued. I should show you the pods, right? So yeah, there's still 1, if I be watching it. Aliases. Yeah, I wasn't fast enough, so it scaled up already because it detected it's above the threshold. The threshold was 30, so it spawned 3 more replicas. Unfortunately, we have only 2 GPUs, so that's another topic, or like subtopic in our talk. How to handle not enough GPU problem, right? Because provided you have 100 GPUs, you just scale the replicas to 100, and it will just work. But we don't have endless number of GPUs. So we can use Carpenter. It's a nice tool that can add new Kubernetes nodes with another GPUs. And it works well with AWS or Azure, but for instance, no solution for GCP yet. Or we can use Cluster API, which I really love, and it's a really open source project. It's harder to set up, but we can scale it with Keda. With this, we have a lot of troubles to solve, like for instance, data locality, because these models are huge. They are like gigabytes in memory. They need to be loaded to GPU, and we need to make sure that the data is close to the code that's running, actually. And also bootstrapping the node, like installing NVIDIA drivers, making sure that images are pulled, and it doesn't take ages to spin up new replicas. And we totally will neglect the load balancing aspect of the problem, because imagine that we have a GPU that is underutilized. We should be probably wanting to having the traffic going to that GPU, and not to the overpressured one. But these metrics can be used for it as well. It can be further improvements. So a couple of words about Cluster API. There are some talks in this KubeCon as well. For me, it's a bunch of CRDs and controllers that can help you with deploying another Kubernetes cluster. But they also have a support for creating those so-called self-managed clusters. They've got CLI called cluster CTL, and you can do cluster CTL move, and then the cluster, in a way, knows about itself, and can scale its nodes, or even upgrade the Kubernetes version and things like that. A nice thing about it is it contains machine deployment, which is a scalable resource. So it has a number of replicas, and you can do things like that, like kubectl scale machine deployment, and say I want 2 replicas. And that's why it clicks well with Keda, because Keda can scale these machine deployment guys. So let's see that in action. I actually have yet another scaled object for the nodes itself. But this one is actually paused. That's why it's not triggering. So let me unpause it. Annotate, not the model one, this one. So it should be false. So now it should start doing something. I can split the screen again. List Kubernetes nodes in here. This is gonna take a little bit longer because it's not that quick. I'll be watching it here. And also I can watch the machine deployments. So remember, machine deployments, shortly MD, is the resource for Cluster API. That's a scalable resource, and we can see there is just 1 replica, but soon there should be more replicas. Right, and meanwhile, I can describe also so already it's clearing up. So detected in here. Now it takes like minutes or 2 to prepare the VM. It's actually talking to GCP cluster, creating VM for us. Then this new VM needs to run kubeadm, join our cluster. It takes some time. And I use, it's called image builder from Cluster API to actually bake those container images into the VM image to make the startup a little bit faster. But for NVIDIA drivers, I'm using GPU operator, which makes it a little bit longer because it installs NVIDIA drivers, and this step takes like 3 minutes. Much better approach would be to compile the drivers directly to the kernel version. But for GCP, I didn't have luck to do that. But it's for further micro optimization, I guess. I can show you the scaled object for the nodes. GPU nodes. And we can see that here the scale target ref is not the deployment anymore, but it's our machine deployment called demo GPU nodes. So it's this guy. And also, nice feature about Keda is that you can have actually multiple triggers in one scaled object. And by default, it takes the maximum value if there are multiple triggers. And one of them is cron-based schedule. And you can see that minimum number of replica for this scale object is 0. But during this time, between office hours, so starting from 10 to 8 p.m., the replica should be 1. So what it actually effectively does is during off hours, it will scale our GPU nodes to 0. It's because they cost money, they are expensive, and your AI experts don't work during night, so why to pay for them? It's still scaling up. Maybe we can switch back to demo, and at the end, it will just work.
Yeah, live demo.
It's going to work, but it takes some time.
Yeah.
So maybe just to sum it up, right?
We have a reference, yeah, just for my company. That's we are hiring, and that's our boss number. And you can reach out to anyone, reach out to me or anyone with a Bloomberg badge or recruiters. And
yeah, same for us. We are on Kedify booth. Come, say hello.
Okay, let's do the thing together. We can go to the question and answer session, and still waiting for the notes to come up for.
The demo is online. It's available online, so everything can be replicated. The cluster API script everything is there.
Do we put our link in our chart?
Sorry?
Do we put the link to our repositories in our chart?
Yeah, this is the link. Like if you want to scale the QR, this is the link for the.
Yeah, it's a very important.
Or there's a short term if you want.
Yeah. Okay.
Yeah. Okay, so I can switch back to demo.
Yeah, and we can switching questions or if you have any.
We can see the node is ready, and now actually the GPU operator will start to do the work. It's not like this, but it works.
Yeah. We have demo, man. First time I think
we have some time, so we take any questions.
Yes. Well.
I have a question.
Yeah.
That went to the mic. We use Keda also. Sometimes when we scale up, it's already quite late because maybe we receive a spike of data and then we scale up. But when we already have our collector going up, data is already going to stable.
Makes sense.
Suggestion how we can
sure.
do this problem?
Sure.
The question in case someone.
Sure. You are asking basically about the stabilization window for. I can describe it in here.
Scale up, I think.
Just one of them. Both of them has it. It's called stabilization window, and you can modify the way HPA actually works because HPA is still being used, but under the covers, it's like implementation detail for Keda. So here we say we have this number that for scaling up, the the threshold needs to be reached only for 1 second. If you increase this number for 100, it means like 100 seconds needs to measure above the threshold, and only then it will scale up. And same goes for scaling down. That's actually a good question because these nodes takes a while to spin up. It doesn't make sense if you measure less to immediately kill them, right? So here we are saying that it needs to be there for, I don't know, 20 minutes or what is it?
Yeah, 20 minutes. Okay.
Yeah.
I think that it's, from the beginning, you show the architecture of cases like this. It's running on top of KDT.
Yeah.
We can use RPS asymmetric. So in this case, we switch to like our custom metric.
Yes.
Yes. So would it be possible to use like RPS asymmetric? In case that here in this case we have only LLM workload, right? But in case if we have another workload that's running,
Sure.
That require RPS can be still.
Okay. I can go a bit with, for example, if you want to use the K-serve to run your serving platform, this is a kind of roadmap we're having now. Say, in the old workloads, we either can scale based on CPU or memory, this basic one. And later, as in knative serving, we can scale based on the number of requests, concurrent requests. But in the large language model, they didn't work for us. For example, I get 100 requests coming at the same time. That doesn't necessarily mean my GPU consumption is high. They do not have that kind of direct correlation to each other. So, like in large language model, there are two kind of criteria you can look at, as we just said. You either look at latency, or either look at the throughput. So, by latency, if they compile or conform to this virtual large language model spec, there's one metric you can look at, which is called the KV cache percentage. It's from 0 to 1. 1 means 100%. It means how much GPU usage you have been used for that KV cache. If it's high, which means I'm actively processing your request, doing inference at the same time. If it's low, which means, OK, that's fine, I can handle. But if it go above kind of threshold, for example, you can set to 50% or 60%. If it go above that, I can scale up for large language model workloads. So metrics collection, we need to pick up the correct metrics to scale our workloads. But for serverless, Well, we can also do that, like with, but that's not large language model workloads. Based on different workload, pick up different metrics and scale based on them.
I'm sorry. Okay. Thank you.
Yeah, thank you.
Thank you, guys.
Thank you, folks. You have a wonderful night.